On a clear night, the stars appear as fixed, permanent points of light. Beneath that stillness, each one is an active balance of two opposing forces, the inward weight of gravity and the outward push of heat. This balance is known as hydrostatic equilibrium. Core fusion creates an outward push of radiation. This perfectly matches the crushing weight of the star pulling inward. Because gravity never stops pulling, and fusion requires finite fuel, gravity will eventually win this struggle. The specific amount of time a star can maintain this balance, and the type of remnant it leaves behind, is determined by a single variable set at the moment of its formation: its mass. This initial weight acts as a deterministic blueprint, dictating the star's entire progression from its first ignition to its final collapse. All stars begin in giant molecular clouds. These are cold, dark expanses of hydrogen, helium, and dust grains that span hundreds of light years. When a shock wave from a nearby event passes through, the gas fractures. Gravity takes hold of these pockets, pulling material into a dense core that heats up as it contracts, forming a protostar. During this early phase, the young star is highly unstable. It emits powerful jets of gas from its poles, clearing away the remaining shell of dust and gas that hid it from view. To become a true star, the core must reach 15 million Kelvin. This temperature provides the kinetic energy needed for hydrogen atoms to overcome their natural electromagnetic repulsion and collide. When they finally collide, they fuse into helium. This process converts a small amount of mass into a massive amount of energy, a relationship defined by Einstein's formula, E equals mc squared. The energy from this fusion creates the outward pressure necessary to halt the collapse. The star achieves equilibrium, and its long adult life begins. This stable period is called the main sequence. While every star follows this path, their lifespans diverge into three distinct tracks based on their starting mass. Low-mass stars, known as red dwarfs, are the most efficient. They are entirely convective, meaning their internal material constantly circulates. This allows them to use nearly all the hydrogen they possess, rather than just the fuel in their core. Comparing stellar mass to lifespan reveals diverging paths. Red dwarfs burn fuel slowly, remaining active for trillions of years, outlasting the universe's current age. Intermediate stars, like our Sun, burn moderately for 10 billion years. High-mass blue giants fuse fuel hundreds of times faster. Consequently, these massive stars exhaust their entire supply of hydrogen in only a few million years. This reveals the inverse relationship of stellar lifespans. The stars that begin with the most fuel consume it so aggressively that they are the first to die. When the hydrogen in the core is depleted, the outward pressure fails. Gravity resumes the collapse, and the star begins its final transition. In low and intermediate stars, the core contracts and heats up until it ignites a shell of hydrogen around it. This massive burst of extra energy pushes the outer layers away, causing the entire star to expand into a red giant. These stars eventually drift apart. They are not heavy enough to fuse carbon, so they shed their outer layers into a planetary nebula. All that remains is a white-hot core, held up by the pressure of electrons packed as tightly as physics allows. Massive stars don't stop at carbon. Extreme gravity compresses the core, fusing heavier elements in concentric shells, neon, oxygen, and silicon. But the process stops at iron, which consumes energy. Once iron builds up, outward pressure vanishes instantly, and internal support disappears. The core collapses in a fraction of a second. The outer layers fall inward at nearly 25% the speed of light, striking the dense center and rebounding in a massive shockwave. This is a Type II supernova. The explosion is so energetic, it can temporarily outshine an entire galaxy, creating the conditions necessary to forge the heaviest elements in the universe, like gold and uranium. The remnants found in a stellar graveyard represent matter pushed to the extreme limits of density and temperature. White dwarfs will eventually cool into dark, inert masses. Supernovae, however, leave behind neutron stars, objects so dense that a single teaspoon of their material would weigh 1 billion tons on Earth.
If the remaining core is heavy enough, it reaches a specific mathematical limit. Research by J. Robert Oppenheimer and others showed that if a core exceeds 3 times the mass of the Sun, absolutely no force can stop its collapse. Gravity crushes the core past the event horizon and into a singularity. It becomes a black hole, an object with gravity so intense that even light cannot escape. While every star eventually loses its balance against gravity, this process is what populates the universe with complex matter. The elements scattered by these deaths provide the material for new stars, planets, and the chemistry of life itself.